Welcome to the Rich Report, a podcast with news and information on high performance computing. Today, my guest is from Cisco. We have Jeff Squyres. Jeff, welcome to the show today.
Hey, Rich, thanks for having me back. It's been a while.
Yeah,
I think we talked about some low latency Ethernet stuff a long time
yeah,
ago.
yeah. So I saw, you had a post on your MPI blog about Ethernet's hidden secrets, and I thought, boy, it'd be great to have Jeff back on and find out what's going on here and maybe learn something.
Cool. Well, thanks. I appreciate it. Yeah, this came about because well, for exactly the low latency product stuff that we've talked about before, and we've introduced supercomputing and stuff like that. I was working on the code for that literally about a week ago, and I wanted to do some performance comparisons. And I said, well, I've got plenty of performance comparisons against my competitors' products, but let's do it against something that everybody understands conceptually is TCP. And TCP has such a terrible rap in the high performance computing community, and not for entirely bad reasons, but I did the canonical TCP tests, and I got a result that I didn't quite understand. And in digging into that, I was like, wow, there's a lot here that I don't think many people appreciate, that I really didn't even know about how complex and optimized TCP is. And with just a tiny little bit of tuning, you can actually get some fairly amazing performance out of good old TCP. And I do want to put a big disclaimer on this. This is not a good idea for the general case, right? The stuff that I'm going to talk about here is not for your web server. It is not for your database server. This is for the fairly special requirements of HPC. And even then, I think your mileage may vary and whatnot. But the point that I wanted to show with this was that, I tweaked basically one parameter on an Ethernet NIC, the Cisco Ethernet NIC, and dramatically reduced my latency such that made it could very well be very interesting for people to investigate. Particularly who have, people who have commodity networking solutions, and they didn't want to go to a one-off specialized HPC type of network, which I think is fairly common for HPC customers today, because the base of HPC is expanding, right? It's not just the bleeding edge anymore. There's this whole missing middle, and growing enterprise HPC customers, commoditized types of customers who are just like, give me a vanilla system where I can crunch a bunch of numbers. I don't want it to have to be special or different or things like that. So this is just a result that surprised me, and I figured I would write a blog entry about it.
Well, why don't we go through your deck here, and we'll do a Q&A at the end, Jeff.
Okay, cool. Well, I wanted to start with just a little bit of background information, because the blog was targeted at a slightly wider audience here, and I have the obligatory, yes, we were talking about supercomputing here, in the obligatory picture of some random supercomputer. I don't even know which one. This is not a Cisco machine room. I don't even know whose machine room that is. And one typical way that a lot of people do this, and of course there are dedicated HPC machines, but a typical way that people do this is that you just have racks and racks and racks of 1U servers running some flavor of Linux and some software layer to bind it all together to make it look like one big honking machine. But it's not really one big machine. It is a lot of individual machines with some kind of network in between them. And this network is used in many HPC applications to send lots and lots and lots and lots of small messages, so they can stay in sync with each other while they're all computing to solve this, computational problem. And therefore, this is the genesis of why short message latency is so important in HPC, and why the network needs to be able to, send a short message really, really quickly from one peer to any given other peer. So in particular, what I'm talking about here is that, A sends to B across the underlying network there. And today's fastest networks, this is on the order of 1 to 3 microseconds, right? And that's a fairly important metric. It is not the only metric, but it's one that people talk about quite a bit. And when I say 1 to 3 1 to 3 microseconds, I'm talking about from user space to across the network, across at least one switch, and then into user space on the other side. And so that's actually pretty amazingly fast. Now, today's fastest networks are typically not Ethernet networks, right? There's all kinds of specific supercomputer networks, and I'm not going to name all my competitors out there. But a lot of these networks are tuned for small message latency because it's so important. But that is changing actually quite a bit. And I'm not going to reiterate a bunch of the stuff that we've talked about with the ultra low latency Ethernet stuff. But again, the customers that are coming on the scene here are not the bleeding edge people. They're the people saying, I just want Ethernet. I want, something more or less the same as what's in the rest of the rest of my data center, so that I can manage it and work it, and I don't have to be a rocket scientist to operate it. So yeah, so this is changing, right? So a lot of enterprise customers are coming on, and they want it to be not entirely different than the rest of their data center, and they want to have an HPC setup that their data center operators can manage with reasonable efficiency and still get good HPC performance. So a big ask that in particular we have gotten at Cisco is just give us better Ethernet, right? Give us Ethernet that is competitive with all these supercomputing networks and so on. And so these are the types of things that we have been investigating. So we have this US NIC based solution. And again, we've talked about it before, so I'm not going to go into detail here, but basically it does the things that supercomputing networks tend to do. It bypasses the operating system. It bypasses the TCP stack. It exposes the hardware directly into Linux user space, so that MPI or whatever middleware it is that you're using can talk directly to the hardware. And that's where you get into this super low latency types of things. So it can send and receive, raw Ethernet frames. There's really very little need for much protocol when you're in an HPC application. You need some, but not a whole lot. And so when you chop out a lot of this processing and you avoid the operating system and you avoid interrupts and all these kinds of things, that's where you get these dramatic reductions in latency. So here's what a typical TCP stack looks like, right? You've got some application at the top, and let's focus on HPC MPI applications here, right? So there's some MPI library in the middle. An MPI library is talking to the sockets library, and the sockets library is going down into the kernel, talking to the TCP IP stack there. And then there's some hardware driver, in this case, the Cisco NIC. We call it a VIC because it's a virtualized interface card, but a NIC driver, and then it actually talks to the hardware itself. Now, on the US NIC side of things, or many of these other supercomputing types of networks, there's a whole bypass going on, right? So you're not talking to sockets anymore. You're talking to some other underlying layer. And in this case, it's the user space verbs library that's in Linux. And what that allows you to do is do some bootstrapping and setup in the traditional kernel kind of way. But then once you get to actually sending and receiving, you're bypassing the kernel and talking directly to the hardware from user space. And again, like I said a couple slides ago, this is where these dramatic reductions in latency come from. So now, with all that background here, let's talk about the results that I got. Like I said at the top of the podcast here, I was doing some performance testing, and I got a result that I didn't quite understand. Right, so I was doing some performance testing with two Cisco servers, and each of them had a 2 times 10 gig NIC, meaning that the little horizontal rectangles that are silver on each of those NICs are 10 gig ports. So each of these cards can do 20 gig is what it comes down to. And I had them hooked up back to back. So I was doing straight performance testing, and I don't want to introduce the variability of a network switch. This is pretty common back-end testing that engineers do. Just do back-to-back, and let's find out what the card and the server is capable of, and remove the variables of switches and things like that. And I was doing a ping-pong latency test. This is pretty common in HPC environments, and most of the listeners are probably going to know what this is. But just to absolutely delineate what we're talking about here, because there's actually multiple different flavors of ping-pong test too. The one that I was doing is called NetPIPE. And basically what it does is it sends a message from A to B. B gets it, and then B sends it back. So there's no overlap. It is a serialized ping pong test. And we do that a bajillion times. Each ping pong exchange is really, really short. So you do, 1,000 of them or 10,000 of them or whatever, and then you divide by N to find out how long that trip takes. Now, specifically, if I do N ping pongs and I divide by N, that's how long it takes me to get one round trip, one ping followed by one pong. And so then what you want to do is on top of when you had the time for one ping pong, you further divide that by 2, and you get the time for one ping or one pong, right? So it's a half round trip, not the full round trip. And we typically call that the HRT, or the half round trip ping pong latency. And again, this is something that's very commonly discussed in HPC types of applications, because this HRT number is indicative of how well your network can do short message latency types of things. So here's a typical test. I did NetPIPE here. Let me orient you to this graph here. The x-axis is the buffer size. So it went from 1 byte up to 8 megabytes. And the y-axis there is time. Both axes are log so that they can fit and scale nicely on here. And what I was seeing is that the time to do an average time to do 1 byte ping pong across one 10 gig port. So I'm not using both 10 gig ports, just one of them, was about 60 microseconds. And as we went up and increased the buffer size, all the way up to 8 megabytes, it took about 150 milliseconds. All right, so several orders of magnitude difference there. And 60 microseconds, I was like, wow, I guess that's a little high, but I guess that's what TCP costs. I said, all right, well, let's run the next experiment here. Let's run it over 2 ports. And what I expected was that the 1 byte latency would be about the same, because you really don't get much of a win of striping, short messages across multiple ports, but you do definitely get a win by striping large messages across multiple ports. So I can effectively, when I'm sending an 8 megabyte message, I can send it at 20 gig instead of 10 gig. And so I expected the 1 byte latency to stay about the same, but the 8 megabyte latency to go down a bit. But instead, this is what I got. I got 1 byte was 30 microseconds. Right now, as expected at the high end, it went down a bunch too, but it really blew my mind. I said, whoa, what is going on here? I don't understand why 1 byte over 2 ports would be half the latency. And this is what kind of started my whole trip down the rabbit hole here, that I had to go learn about how TCP and Ethernet works a bit here. So let's review the facts here, right? And this is a blow up of that same graph here, but up to about 2K instead of 8 megs. And you can see another interesting point here is that from 1 to 1024 bytes, the half round trip latency is absolutely flat, right? It's about 60 micro and about 30 micro for 1 and 2, 2 and 1 ports, respectively. And I said, wow, what is going on here? Why is it flat? And why is it half the latency when I'm using double the ports? All right, so let's look into about how TCP works, and really, actually, kind of more generally, this is how Ethernet works. It probably would have been a better slide title to say this is how Ethernet works. Let's say that a frame arrives at the VIC itself. Now, the NIC sends an interrupt to the OS Ethernet driver, and the Ethernet driver in Linux wakes up and says, oh, okay, hey, I better copy that packet from the RAM on the card to main RAM. And then it hands it up to the TCP stack, who hands it up to the web server or the MPI application or whoever it is who needs to get that packet. Okay, so that's generally what happens here. But let's look at what's called the Costco Rule, meaning it's always better to do things in bulk. Why do things one at a time when you could do n things at a time? So in particular, this transfer here of both the interrupt and the data from the NIC to the server RAM itself, let's optimize this a bit. So instead of copying one packet at a time, let's copy a bunch of packets across PCI at once. Take advantage of the amortization of overhead when you copy in bulk. And likewise, you only need to raise one interrupt instead of n interrupts, right? So you can send one interrupt for a whole pile of packets rather than n interrupts, one for each. This is known as interrupt coalescing, and I don't want to say that this is Cisco optimization. Every Ethernet card on the market does this today. This is a very, very common thing, and it's got that name, interrupt coalescing. You'll see it on just about every Ethernet card on the market. So let's look at, with that optimization, how does this actually go? So same first step here, an Ethernet frame arrives, but now the NIC says, well, wait a minute, has X amount of time here passed since I sent an interrupt? And if the answer is no, well, then it just queues up the frame. But if the answer is yes, then it sends up all the queued frames and an interrupt to represent, one interrupt to represent all those queued frames. All right. So Well, that's great. I mean, that is a fun little lesson there. But how does this affect my result here? Well, let's look at what's going on here. This screen here is the management screen for a Cisco UCS server. And in particular, this section right here is the properties of the NIC itself. And we could actually go in and change some of these things. And this is what I was referring to. I'm going to change the coalescing timer. The timer we default when we send these things out is 125 microseconds. So if you look at, that's what I kind of highlighted there. It might be a little small on the screen, but 125 microseconds. So let's look and see exactly what that means here. So if we look at a ping pong with this 125 microsecond timer in mind, this is what's going on. Let me orient you to this graph a little bit here. I have two servers, well, more particularly two NICs, right? A and B. And the dotted lines represent 125 microseconds. So for example, when A sends a ping frame to B, we see it gets across the network and it's received at the NIC, a relatively short amount of time later, right? But it actually sits there on the NIC and doesn't go to the OS until the remainder of that 125 microseconds expires, right? So it actually sits there dormant, doing nothing for a while, right? Eventually that coalesce timer expires and B sends the interrupt and the operating system gets the frame and it goes all the way up to NetPIPE and comes back down. And a short while after that, NetPIPE sends the Pong back. You see there's a little gap between the dotted line and where the Pong line starts and so on. That's when all the processing occurs in NetPIPE and things like that. Right. And you repeat this out and so on so that, the same thing happens on every time, right? That the packet is actually getting over there fairly quickly, but we're being dominated by this coalescing timer on each side. And this happens for every single ping pong that goes across. So for example, in this case here, we have 4 ping pongs and it takes about 8 times the timer duration, right? Even though the network is actually quite a bit faster than that. Right. So now, again, I want to stress something that I said at the very beginning of the podcast here. In general, coalescing interrupts is a very, very good thing, right? You want that for things like web servers, database servers, SSH traffic, all this kind of stuff, because you don't want to bombard the CPU with interrupts. An interrupt is a very eventful type of thing on your CPU. It disrupts caches. It causes pipeline stalls, does all kinds of things like that. So this interrupt coalescing that Ethernet NIC hardware developers put in is generally a very, very good thing. But here in the HPC case, it really does hurt your short message latency, right? Because we have fairly specialized requirements that we want for HPC applications. So how can we reduce these artificial delays? Well, you probably kind of guessed it. When I showed it before, when I'm doing 2 ports, well, think about what happens with the hardware timers. They're never really completely in sync, right? So really, when I take advantage of using 2 ports, I'm using 2 timers and I basically get the overlap of those timers. So I'm not going to flip through every single arrow here, but you look at the pattern here, the timers are not completely in sync, and so I get that overlap, and therefore the average of all my ping pong latencies goes down because I'm taking advantage of exactly this kind of asynchronicity, right? And it's actually even less clean than what I put on the slide here. What I put on the slide here was that NIC A and B on their individual ports are lined up perfectly with their timers, right? The dotted lines are exactly vertical. But that's never true either, right? So in reality, I've got 4 different timers going here. And when they all overlap like that, you get a higher degree of asynchronicity, you get a higher degree of overlap, and you actually get, very nice reduction of overall latency because you're bouncing between 2 different NIC ports with 4 different timers, right? So in this case, the asymmetry was actually so good that it reduced my 1 byte latency. When I flip flop back and forth, I do 1 ping pong across 1 port, 1 ping pong across the other port. My average latency went down to 30 micro. Now the individual ping pong latencies really stayed the same, okay? But what we did was we decreased the time between them, right? This is average latency that we're talking about here. We get higher throughput, because we're reducing the gaps between each ping pong, because I'm taking advantage of the asynchronicity of the interrupt coalescing timers on the different ports. All right, now let's try something else. And if you saw before that, the properties in the Cisco UCS manager here allow me to actually change the coalescing timer. It's not just reading it that it's 125 micro. Let's change it to 0 and see what happens. Now, what this means is that for every individual packet that comes into the NIC is going to immediately raise an interrupt and trigger that sequence of the OS driver copying the packet over and things like that. It's never going to delay at all. And just to jump straight to the punchline here, you can see that the latencies drop down dramatically, right? So for one port, we get about 10.5 micro, and for two ports, we get about 10.6 micro. And this is very much what I would expect, that the latency is tremendously lower. And when I add a second port, MPI actually has more places it's got to check for incoming traffic. So the latency should go up just a tiny little bit. So these results here are much more in line with what I was expecting to see. A, significantly lower latency. B, when I add a second port, I add a tiny little bit of latency on there. And this gives me much more of what the capabilities of the network are itself. Now, there's still quite a bit of extra time in here, because 10 micro, in supercomputing terms, is still, quite a bit. With our US NIC latencies, we're getting down around in the 2 and the 3 micro range. So the network is actually capable of doing that. This extra, 7 to 8 micro is the TCP stack and the interrupt and the trapping down in the kernel, all those sources of overhead. So you can't get rid of all of that, because by definition, it is TCP. And if you're using the operating system TCP stack, that's just how it works. There are people who have user space TCP stacks. I'm not really going to talk about those today. But here, just plain vanilla TCP, change one parameter, get dramatically lower latency. Now, another thing that's interesting to note is that even at the high end, this surprised me a little bit too, even at the high end, it maintained actually pretty darn good performance. I was kind of expecting the performance to tank when we're sending an 8 megabyte message, and every single frame of that 8 megabyte message is causing an interrupt. But it actually stayed on pace pretty well, right? Two ports, we got down to about 5.5 milliseconds, and one port at 7.2 milliseconds. But it was still actually faster than when we were using the interrupt coalescing timer. I expected it might actually get worse. The lines might cross, but they didn't. So that was actually kind of pleasing. All right. Now, this is great. This is a little stunt, right? But what are the trade-offs here? Because this is engineering after all. There's no such thing as a free lunch, right? Well, let's look at the pros first, right? Obviously, you get much faster TCP latency without changing your application at all. You made one hardware tuning and bam, your app went faster. That's cool, right? And the faster speeds seem to scale up to the large messages. Like I said, that was a pleasant surprise with modern Intel-based hardware server platforms. It actually compensated for getting so many interrupts. So this is obviously a very good win for low latency applications with sparse communication patterns. And it's definitely best for the NICs that are dedicated to MPI traffic in itself. You wouldn't necessarily want to do this on the network interface that's also serving, say, NFS or NTP or SSH and all your other services traffic and things like that. If you've got interfaces that are dedicated to MPI, this might be worth trying out there. All right, so that's the rosy side. Let's talk about what are the drawbacks here. Well, this may not scale very well if you have lots and lots of MPI processes who are all beating on the network pretty heavily, because you might very well be beating on, the interrupts that are being risen might kill you, right? But then again, we were sending 8 megabyte packets and saturating the TCP pipe, or saturating the network pipe, and it was still doing okay. So that might actually represent an upper bound. I don't know. Some experimentation might be necessary here, but it's definitely worth noting that it might be worse when you throw more and more processes in. This was a simple ping pong test. This was not a real world HPC test. It was a micro benchmark. So it was a good data point, but more study is necessary. And like I said, lots and lots of interrupts are going to socket 0, core 0, right? So you might actually need to dedicate a core to TCP, right? Let your MPI run on N-1 of your cores, right? So if you've got a a Sandy Bridge modern server, use 16 instead of, I'm sorry, use 15 instead of 16 cores, right? And you might want to direct your MPI to completely avoid socket 0, core 0, bind all the processes elsewhere and things like that, or even move the interrupt affinity somewhere else, things like that. So you might have to give over a core to your communication stack. I don't know. More experimentation is required, and your mileage very definitely may vary. It depends on your application. It depends on its communication patterns. Heck, if your application doesn't even care about low latency, it's not latency sensitive at all, then this will be a zero win for you altogether. But if you have an app that's sensitive to latency, as many HPC applications are, then this could be a win. Now, there's other things that you can do here too, right? Like I said, let TCP take over core 0, but this is not a binary solution, turn it on, turn it off. There's a whole spectrum to play with here. One obvious thing you could do is, well, we don't have to set that timer to 0. You could set it to, say, 5 microseconds. Something less than 125, but greater than or equal to 0, and see how that does, right? Maybe, letting it coalesce a little bit will let you have better bandwidth and not kill your latency. These are things that somebody could play with and see how it goes. But again, the whole point here was that a lot of people think that with Ethernet, you can't get good performance, right? But that is just not true. You look at some of these low latency Ethernet products out there that are coming out from my company and from my competitors and things like that. You can definitely get down into the very low single digits range, right? But even when you can do low latency, let's differentiate ultra low latency versus low latency with one parameter tweak on TCP, that really goes to show the power of how good TCP is. It's amazingly fast and very well optimized. Don't forget, the HPC community tends to eschew TCP quite a bit, but the whole rest of the world runs on it. And so the whole rest of the world has spent the last 15 years optimizing TCP to be really darn good. There is a lot of TCP offload on every NIC that you buy today. It's not a full TCP offload engine, but there's a lot of operations that you could say, dump a 4 megabyte send, and the initial parts happen in the software, and then the bulk of that 4 megabyte send is just handed off to the hardware, and it can just do the whole TCP transactions right there on hardware. So it's very few assembly instructions before that 4 megabyte send is just dumped to the hardware and then handled from there. And that's surprising to a lot of people who don't pay attention to Ethernet, to know that it has these kinds of powers in there. So the real bottom line here is that TCP is a great and highly optimized protocol by the rest of the world, but it's typically tuned for general traffic patterns. It is not tuned for HPC. So if you've got, an HPC specific TCP link that you're using for your MPI stuff, you might want to investigate tuning it and see if you can actually get a little bit of a win, basically for free. And that was pretty much my whole message here, is that TCP doesn't suck as much as you think it does. So go play with it and see what you can get.
Well, that was good, Jeff. Thanks. I guess you've asked a lot of the questions for me here, but as part of your experiment, you by having those dual ports, right? You stumbled upon this this capability to reduce the overall latency, right? So so you're not saying add a second port, because that would actually increase the latency, correct?
Yeah, in my case, I was, able to do that basically for free, because I'm the hardware vendor and I have plenty of switch ports and I can do whatever I want, right? But, in a real world scenario, most customers only wire up one port, even if they have a multi-port NIC.
Right.
And so, yeah, I did make the point that typically when going across multiple ports, yeah, it can be a bandwidth multiplier, but typically it does have a minor impact on your latency, if nothing else, that because your MPI has to monitor both ports. And so, checking for incoming messages in two places always takes longer than checking for incoming messages in one place. So it's pretty easy to understand why the latency goes up. And even when I had that one parameter tweaked down pretty low, it was a 0.1 microsecond change. And I think in some of the even lower latency networks, it's less of an effect than that. But the point is, it's not completely free.
Right, right. And then as you you decrease this coalescing coefficient number, right? I mean, the core is continually getting interrupted in this kind of scenario, right? So it
Yep.
isn't able to do much else, I would guess.
I would think so. And again, I was just doing a simple ping pong test here.
Yeah.
It would really be great if somebody did some real world application testing types of things. I it's hard for me to justify being able to do that because I'm focused on stuff below TCP, and so I was just
Mhm.
trying to get a comparison number. I'm not going to do an exhaustive test on it. But yeah, you might very well have to give over that core to the TCP stack entirely and have your MPI job just use n minus one of the cores in your machines. You might have to sacrifice a core, but if that actually gives you an overall better win because your latency goes down and you have a latency sensitive application, that could still be a good thing.
Yeah. So Jeff, just in rough numbers, what kind of speed ups might be possible with this? I mean, we saw a latency go from what 60 microseconds down to 10.
And yeah,
So with multipliers, that could be a significant application speed up if it fit the profile, couldn't it?
absolutely. And you can tell where that 60 number came from. And I was very careful on all my slides to say approximately 60.
Yeah.
The coalescing timer defaulted to 125, right?
Yeah.
So basically, a round trip was 125 microseconds. And then, NetPIPE is looking at the half round trip. So it's approximately 125 divided by 2. So it was approximately 60 micro. And that is directly related to that coalescing timer. And so, if whatever hardware your listeners have, if you're able to go play with that coalescing timer value, I would encourage it. Go see what you can find. And again, for your MPI traffic, not for your NFS or your SSH or other stuff like that, but pretty much for the MPI traffic, see if you can play with that timer. And there's also, I didn't even talk about it. There's 10 other parameters that you can play with that all have very subtle effects on how things are sent across the network and resource utilization and latency and things like that. This was just the biggest bang for the buck that was easy to make a slideshow about and talk about.
Yeah, yeah. Well, you make a good point. I mean, TCP out of the box, it was not optimized for HPC, and you can get in there and turn these dials, and there might be some definite benefits to trying that out
Yeah, for free, right?
for
No
free.
change your
Yeah.
app, no change your network. It's basically changing one parameter, and it's like, holy cow! Now I've got a low latency interconnect. What can I now do with that? That's
Well,
cool.
yeah. So Jeff, if we got folks out in the audience and they get big performance gains, I guess we should have an address where they can send you a six pack of your favorite beverage. I think.
Just go to your local Cisco office and hand it into the reception desk.
Okay.
I'm
Yeah.
sure they could find somebody who will consume that and say thank you very much, sir.
Thank you. Well, great. Well, Jeff, I want to thank you once again for coming on the show today.
All right, appreciate your time. Thanks, Rich.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high performance computing.